Okay, so how are you today? This is last week for the spring semester, right? So, and next Friday we have a final exam. You remember? Okay, so today let's talk about plastic hinge. So in the last class, we studied about plastic bar, right? Plastic hinge. Today's topic is plastic hinge. Okay, let's consider some beam which has a cross section, rectangular cross section with a 8H and width B. This is cross section, and this is a part of beam will subject to the bending M. This is positive bending moment applied. And let's consider Euler beam theory. Then strain in x direction, so beam length direction equal minus y and curvature. This means curvature, right? So if you look at this equation, the longitudinal strain xx is a linear through the thickness of the beam, right? And bending moment can be calculated from the stress distribution dA, right? And this stress xx. Okay, if you multiply Young's modulus here, you can calculate stress xx. So stress xx equal E xx in the linear analysis. Linear case. But in nonlinear case, this condition doesn't hold. Okay, so this is basic equation we need to remember. And now let's consider elastic and perfectly plastic material behavior. So here, strain xx here, let's just strain, okay, xx, stress xx. And this point, sigma 0, and this point E0. Here the sigma 0 is yield stress, and E0 is elastic limit, strain of elastic limit, right? Of course here minus sigma 0 minus E0. Now I like to increase the stress. Okay, so when the strain is I'm going to increase strain small. Let's say this strain is E0, limit strain. Okay, and this is a strain, first strain state A. Okay, let's increase the strain. Okay, until E0. Then this is a next strain state, B. So here strain is smaller than elastic limit, right? And now strain go to the elastic limit. And then if I increase the moment more, then strain will bigger than elastic limit, something like that. Let's say this is a C and D, last case. Okay, really, really big strain. For example, this is a almost here E0. So now I like to consider these four cases. Then I can calculate the corresponding stress distribution. So corresponding stress distribution. When the maximum strain is smaller than elastic limit strain, okay, stress is stress distribution is also looks similar, and here sigma 0, right? And when the strain reach to the elastic limit strain, the maximum stress will be sigma 0. Okay, something like this. And next case, what happened? Strain is bigger than elastic limit strain. What happened? So here, strain, here we have some strain part which is bigger than elastic limit. So strain is bigger than elastic limit somehow here. So strain shape is changed. Okay, and at this part, okay, this is a sigma 0. Shape is changed like this. Shape is not just a triangular shape. How about the case strain is really, really big? Sigma 0. So this is asymptotic case. So when we have a stress distribution like this in this section, we are saying this is a plastic hinge. Plastic hinge occur. So stress distribution or plastic hinge. So this plastic hinge, the stress distribution will give us maximum possible moment of the section. So here we have saying this is the moment corresponding to this distribution is MEL, and moment corresponding to this distribution is M0, and name of M0 and MEL is that M0 MEL elastic limit moment. M0 is a plastic limit moment. Over there from case B and case D. So plastic limit moment is a maximum moment of the beam cross section. And here curvature. Let's plot the moment curvature curve. Curvature. This is a curvature. So until the elastic limit moment here, MEL, as the curvature increase, the moment linearly increase, right? From here to here. And this is a M0. M0 is a maximum moment. And then moment is gradually increase. And this is a maximum moment here. This is a typical curvature moment curvature curve. So moment curvature curve. Okay. And from here to here, this is a curved area, so transition area, right? And for the analysis of real structure, people like to use the more simpler curve. Looks like this. This is M0. This is idealized moment curvature curve. Because in the analysis, it's very hard to consider this part. So originally part should be like this, but people like to use this simple to linear curve. So any question? You understand these stress distribution? But here we should remember, in the beam theory, the basic assumption is that cross-section should be plane always during the deformation. So this is a cross-section, original cross-section and deformed cross-section. So because of the deformed cross-section, should be always the plane, so should be straight line, and the strain should have also linear distribution through the thickness. But stress can be this kind of distribution. It's not a linear distribution, right? Okay. Okay, let's consider simple beam case for the understanding of the plastic behavior beam. At the center, we apply force F. Okay, then I'm going to increase that force little by little. So where is the maximum place? Where is the place where the maximum bending occurs? Center, right? Here, maximum bending, M max will be 4 FL, right? L is the length of the beam. And this is a center line. Where the first plastic strain happened? Where? Where is the place maximum stress happened? 정호, where is the place maximum stress happened? Of course, center, right? And top or bottom or center, maximum stress. Where is the place maximum stress happen? Maximum stress happen this point and this point, right? So as the moment increases. So here the applied force F increases. First, plastic strain happen at this area and this area for the first time. And then this area increase. Something like that. This is a plastic area. Okay? So this plastic area grows. And then finally, if this plastic area cover all the cross section, something like that, cover all the cross section at the center, this big part become plastic hinge. Here, plastic hinge. So plastic strain happen at the place where the maximum stress happen, right? And then the area grow from that point. And if all the plastic area cover the full cross section, okay, this cross section become elastic hinge. So, for example, let's say here is a section A, here is a section B, and here is a section C. Then section A. At section A, the stress distribution is this. This is a section A. Okay? And how about section B? Section B. Okay. Section B. This is a section B. and B. Section C. This is section C. Okay, so you understand here? Now I'd like to ask you when this beam collapse. Collapse. What's the definition of collapse? When does this beam collapse? So, here I have a beam. This is a beam, right? One beam. And this is a center. So I'm going to give some moment, okay? I'm going to slowly increase the moment. And at certain applied force, it become folded very quickly. Right? That means collapse. Collapse means the rigid body motion. So if the structure is properly supported, prescribed, then rigid body mode cannot occur, right? Cannot happen. But if the dead body fail, some part is fail, then, and it can make a rigid body mode, then we are saying this is a collapse. Okay? So it's different from the material failure. So when we define the material failure, here, this 1 point yield, then we are saying this structure fail. But collapse is quite different. If the whole of this section yield, then start to move. So there will be a dynamic behavior. Okay, then it collapses. So that collapse load can be very easily calculated for F critical. Let's say F critical is collapse load. L collapse load equal M0. And F critical equal 4M0L. This is a collapse load. So how this beam collapse? Here at the center, this is center. It collapses like this. Like we have a hinge at the center. F. Okay? So all the displacement is concentrated on the center. It collapses. The beam is folded. We are saying this is collapse. So originally this one doesn't have a hinge at the center, right? So this one can support F, external force F, without rigid body mode. And when we have a hinge at the center, right, it's a stable structure. It's not a stable structure. We cannot analyze, right? So once we have a hinge, so you can consider the problem here. This is beam with the hinge at the center, and I'm going to apply the F. Can you solve this problem? No. We cannot solve this problem, right? Because this beam cannot support the load F because of the rigid body motion. So we cannot solve this kind of problem. So when we the system can allow some rigid body motion. So we are saying the system is collapsed. Understand? Okay, so that collapsed load will be a maximum force, limit force. Okay? Maximum force. You remember Seongsu Bridge collapsed, right? It cannot support any the additional load, right? It collapsed, permanently collapsed. So, material failure or structural failure is different. So when you can record the material failure. So stress at some point become bigger than strength. We are saying material failed. So material failed at at this point, right? So only this part is fail. And this is a whole structure. Even this part fail, whole of this structure doesn't fail, right? Still can support the load, right? But whole of this section is fail. Whole of this structure cannot support any additional load. So it means structural failure. So what I like to say is that material failure and structural failure is different. Okay? What's different, 정호, between material failure and structural failure?
Structural failure means it can't resist the flow.
Okay, so other understanding is this. Material failure defines the space of stress and strain. So material pain, when the stress reaches to the strength. But failure of structure is defined on the force and displacement level. Here, let's say the force is here and displacement is V. Then force displacement curve will be like this. And this is the maximum curve. So L for LZ. This is F critical. Okay? And material failure happened from here at this point. This is an elastic limit. So material failure happened from this point. Even material failed, structure doesn't fail, and structure finally fail at this level. Okay? So there are several design methods. Some methods say when the material fail, we can say the structure also fail. Okay? That's the one of the design method. So allowable stress method, AST, and the other design method is considering the limit load. Okay? Limit design analysis. Allowable stress design and limit stress design, something like that. Limit load design maybe. Okay, so in the design of stress, it's very important to know the limit load, collapse load. Okay? So now I'd like to show you how to find that limit load. Okay? First one is incremental analysis. So this incremental analysis can be done by the commercial finite element software code. Of course, the problem is simple. We can do that by our hand calculation. Okay, so I'm going to show you the example of limit incremental analysis by solving some simple bar problem. Let's consider bar problem which has a 3-member. Okay. Actually, this problem is not that simple. So okay, we have a 3-bar, and I'm going to. This is force F is applied here, and displacement here V and U. This is the problem we have. And so behavior of the material is like this. P is a tension force and E is a stretch. 1E P0 minus P0. P0 is a plastic force of bar. And I'm going to increase. Here time F, step by step, or we can say step. Increase the force very slowly because this is static analysis. So we have a bar, let's numbering the bar. 1, 2, 3. We have a 3-bar. So this incremental analysis procedure is quite complicated. So initial step. Let's say F0 equals 0. So initially the applied load F is 0. Okay? Initial step is represented by the here's superscript 0. Okay? And U0 equal V0 equal 0. Initially, displacement is 0. And P1 equal P2 0 equal P3 0 equal 0. So member force of the each bar is 0. Okay, initial step looks simple. And step 1. Next, step 1. Step 1 is this. I'm going to solve this problem. This bar problem with the incremental load delta F. So I'm going to apply delta F. So, and each bar have a bar force delta P1, delta P1, delta P2, delta P3. I am going to analyze this case. So we have a 3-member. So this is simple problem. You can solve this problem, okay, by using principal virtual work and some other direct method. So for this system, stiffness this is the stiffness of the system initially. So delta U, delta V. 0, delta F. I don't want to show you how to calculate this matrix because you already know how to do that, right? So once we solve this system, we can calculate the delta U, delta V, right? Right? Then we can calculate delta P1, P2, P3, right? Is that right? We can solve this system. So we can calculate displacement and member force, right? Then member force delta P1 equal delta F, delta P2 equal delta F, delta P3 equal delta F. And because this is the first stage, so initially this is P1. Initially P1, P2, P3 was 0, right? So each member force can be expressed by external load. So now I'd like to ask you, which member failed first? So which member failed first? 2. This is your biggest number, right? So we can think this member will fail first, right? So everybody can expect, right? This member fail first, right? Okay, then let's calculate the failure load corresponding delta F. So from this equation, delta F equal 1.71 P0. Because at this point, this becomes P0, right? Failure of member P2 means the member force of member 2 becomes same to the plastic limit load. Okay? From this here, we can find the delta F. So delta F, the incremental force when the member 2 fail. Okay? Okay, then also because we know delta F, we can calculate the delta U. Okay, let's calculate delta V equal 2.4 EA LP0. Something like that we can calculate. And also we can calculate all the member force and displacement. So if I summarize, okay, F1 equal F0 plus delta F equal 1.71 P0. U1 equal U0 plus delta U equal minus EA LP0. V1 2.4 This is fair. So if you look at this result, member 2 is fair, and member 1 and member 3 have a member pole smaller than P0. Limit poles P0, right? So next step is really important. The first step is everybody calculate this first step. In the next step, you need to understand concept, how to analyze this. When we have a failed member. At the first step, we don't have any failed member, right? And now we have one member fail. How can you analyze this system when we have a failed member? Okay, so we have a 3 member. But when the second member fail, P0, P1, P3, 1. This is F1. Even if this is a case of the end of the first step. So this member 2 always give the force P0, even it's stretched more, right? So it can be modeled by just force P0, right? Applied at the point here. It can be modeled by the force. It's not a member anymore, right? It behaves like this. And at this situation, this system is in equilibrium. Okay? So even I increase the force, I added the force F more, this member 2 cannot contribute to support this additional force. So additional force can be supported by only member 1 and 3. Okay? This final concept is important. So at the step 3, step 2, we need to analyze delta F, delta F, delta P1, delta P3, and delta P2 equals 0. We need to analyze this system. So here we have only two members. So ordained general force that F is applied can be supported by only two members, and delta P2 should be 0. Okay, this is a really, really important physical concept you need to understand. So structural system is changed. Okay. So stiffness is changed too. Delta U, delta V. 0, delta F. So stiffness is changed. So this is stiffness. Without contribution of member 2. Right? This is important. So you can think we lose the member 2. So actually I need to continue this analysis of this in the next class. Okay, so I like to summarize. Any question?